Yeah, just give me a minute. Yeah, okay, now the recording has started. Yeah, so uh, we have, as far as the topics are concerned, we have covered quite a bit of or at least the essence of all the topics, except possibly Z transform, which is the last class, which is the last unit, which I thought was not necessary at this point because first of all there was not enough time, and also this Laplace transform, which I covered additionally in the last week, that is a generalization of the Z transform. So if you get the idea of what the Laplace transform is used for, you can use it in the Z transform. But I personally feel that for this particular course, it is more important that we focus on Fourier analysis. So that is why most of the topics we covered were on Fourier analysis. Okay, so there are no additional topics which we will cover. Whatever is there on the YouTube channel. Whatever topics are there in the YouTube channel is what is there. And so in terms of textbook, if you look at Oppenheim's book, it is essentially chapters 1, 2, 3, 4, 5, and 9. This is what we have covered from Oppenheim's textbook. Okay, 1, 2, 3, 4, 5, and 9. That you can see from the material which is there on YouTube. Fine. So, so I am planning 1 or 2 revision lectures, which gives like a very quick overview of some of the things which we covered. And after that, I will start giving you the problems. Okay. I will give several problems. Not all of them will be part of the problem sheet. But now, what I'm thinking is during this revision period, I will be online. Yeah, so I will be online during this time. And if you try to attempt the problems, and if you are having difficulty in solving some of the problems, that time we'll discuss in this Google Meet session. Fine. Okay, and this will also help you to solve that problem sheet. Okay, so that is that. If you have any concerns or suggestions, you can type or you can chat here. Tutorials we had covered 4 on Moodle because I had not asked you to submit anything. I am hoping that you guys have worked out the solutions. Okay, and some of the problems will also be from tutorials which you have solved already. So some of the problems you can directly get from there, but some of them are of course new problems. So please look at that. I think the solutions of some of them of all the tutorials have also been uploaded on Moodle. That also you can see. Fine. So the summary of this revision period is that we will have live interaction. We will have a few lectures, which I think, based on how you guys respond to the problems or the kind of questions you are asking, we will have more lectures if needed. Again, but it will all be topics which we have covered already. Okay, so there are no new topic going to be covered now. And I think also the guidelines also say that, so the revision period is till the 21st. So all the submissions will happen after that. So there is enough time. Okay, I'll give you enough time so that you don't have to worry about meeting deadlines. You sit and solve the problems, take your time and solve the problems and submit it maybe around 25th or 26th or something like that. We'll see. We'll find out a mutual date. Could the weightage of the tutorial sheets be increased? Okay. See, already there are 40 marks for the tutorials. Okay, I will see. Okay, I will see whether we can make it to 60. I'll just have a look at again how to do the weighting, and then we will see. Fine. I guess all people agree to this, that they want more weightage on the problem sheets than on the final exam, on the 2 exams. Right? Yes. Okay. I'll see what to do. I'll see. So maybe I'll try to make it a little higher weightage to make it 60 or something. Okay. Okay, sure, sure. I got the point. Fine. Okay, so I want to just summarize some things which we studied about Fourier analysis. So the four different topics on Fourier analysis which we studied, I want to summarize again. So I have made a small set of slides, handwritten notes, which I will upload again on Moodle. You can have a look at that. But I'm going to share this. So this will take only 10-15 minutes. I'll share it with you so that you can see. Okay. Can you see these slides? Hello, can you see the slides? Okay. This PDF, frequency analysis of signals and systems. I hope you can see that. Okay. So shall I go ahead with this? Okay. Okay, so so this is about frequency analysis of signals and systems. This we covered across several chapters. About 3 separate chapters were there. So this is only a summary of that. Okay. So to do frequency analysis of signals and systems, we looked at 2 types of tools. One was the Fourier transform. Can you see my pointer? Okay, you can see this mouse pointer, I hope. One was we zoom in. Okay. Wait, let me input it to this screen. Hold on, let me move my meet window here. So this will not be able to see otherwise. Can you see it now? Is the zoom okay? Zoom is fine. Okay, fine. So frequency analysis of signals and systems, we looked at 2 types of tools. Okay, one was the Fourier transform, and the other was the Fourier series. Okay, so the Fourier transform is defined for finite energy signals. Okay, that means if the signal is a continuous time signal, it means that the signal is square integrable. Okay, because see, I'm not able to write right now because my tablet is not supporting the meet. But when I say it is finite energy, you should understand what you mean by signal energy, which is if you have x of t as a signal, a continuous time signal x of t, finite energy means when you do minus infinity to plus infinity integral of x of t absolute value whole square dt. Okay, that is less than equal, that is less than infinity. That means it is a finite, the energy of the signal is finite. These notes I will upload after this class. I will upload this on Moodle. right? But all these things are already covered in the lectures, and the corresponding notes are already there on Moodle. Right? So these are finite energy. That means if it is a continuous time signal, it is x of t the whole square minus infinity to plus infinity. When you do this thing from minus infinity to plus infinity, dt x of t the absolute the whole square dt. Why do we take the absolute? We take the absolute because x of t could be complex. Okay, so it could be a complex signal. So that is finite energy signal, right? And if the signal is a discrete time signal, then it is a summation x of n the whole square, n going from minus infinity to plus infinity. That summation is the energy of the discrete time signal. So for such signals, the Fourier transform exists. We also saw earlier that this condition that it has to be finite energy signal is a sufficient condition. It is not a necessary condition. So that means there are signals which do not have finite energy but still has a Fourier transform. Okay, that we saw the case for periodic signals. Periodic signals are signals which have infinite energy. They are power signals. I hope you remember the difference between energy signals and power signals. Okay. So a periodic signal is a power signal. That means it has infinite energy. But such signals also have a Fourier transform. So finite energy requirement is a sufficient condition. It is not a necessary condition. So that one of the tools which we saw was the Fourier transform, which was defined for finite energy signals, and the other other tool which we saw was the Fourier series. The Fourier series is defined only for periodic signals. Periodic signal means the signal will repeat. Okay, so when you have signals which are periodic, you can have what is known as the Fourier series of that signal. So what does the Fourier transform and Fourier series do? It decomposes the signals into sinusoidal or complex exponential components. So basically, you are representing any x of t in terms of sinusoids, that is sines and cosines, or in terms of complex exponentials. Complex exponential and sine and sinusoids have a direct connection. What is the connection? The real and imaginary part of a complex exponential is a sinusoid. Okay, both the real part is also a sinusoid, and the imaginary part is also a sinusoid. So that is why there is a strong connection between complex exponentials and sinusoids. So basically, the tools of Fourier analysis allow you to decompose any x of t into either sinusoids or complex exponential signals. Right. So when we have, let's say, a continuous time periodic signal, it is periodic, right? So it has a Fourier series. So first of all, why are they useful for LTI systems? Because the Fourier analysis lets us represent a signal in terms of complex exponentials, and complex exponentials, or sinusoids for that matter, are eigenfunctions of LTI systems. So we learned about linear time invariant systems, right? So if you give e raised to j omega t as input to an LTI system, the output will be exactly the same e raised to j omega naught t multiplied by a constant. This h of omega naught is a constant. Okay, this is constant because it does not depend on t. So if your input is e raised to j omega naught t to an LTI system, your output will also be e raised to j omega naught t multiplied by a constant. That is why it is an eigenfunction. So it's like a eigenvalue eigenvector. No? So if you consider this as the operator, this is your x, ax equal to lambda x. This is your lambda and this is your x. Fine, and this h of omega naught, because this is a complex number, that I can write it as a e raised to j phi. Phi is the phase. Okay, so the output will essentially be a multiply your e raised to j omega naught t, which is modified by a phase factor. So it will be e raised to j omega e raised to j omega naught t plus phi multiplied by a. That will be the output. So essentially, if you give this the complex exponential as an input, you get the same complex exponential output back. So the frequency content is not changed. So because this system is an LTI system, a linear combination of harmonically related complex exponentials like this, that is, this is nothing but a linear combination of harmonically related. So we learned about harmonically related complex exponentials. So there is, so consider right now this k is not there. Suppose there is only e raised to j 2 pi f naught t. Okay, so that is one complex exponential having the frequency 2 pi f naught. Now, if you take multiples of that, that is 2 pi k f naught, k goes from 1, 2, 3, minus 1, minus 2, and so on. So those are, so the other, the resulting complex exponentials are known as its harmonics because they are multiples of the fundamental frequency, the 2 pi f naught. So if you are able to represent your x of t in terms of harmonically related complex exponentials, then the resulting x of t. So if you take one complex exponential, take all its harmonics, and then you add it together with some constant factor for each exponential, you will get some output xt. Now this xt will also be periodic with the period same as that of the original complex exponential you started out with. So this x of t will also have period, will have frequency 2 pi f naught. And since it is periodic, having the period, having the frequency 2 pi f naught means the period is, here I have written the period as Tp. Tp is equal to 1 by f naught. Okay, so the frequency and period are inverses of each other. So this is essentially how you are representing x of t in terms of a Fourier series. You are representing, given a periodic x of t, you can decompose them into harmonically related complex exponentials where the fundamental frequency, that is the basic building block, has the same period as your given x of t. And how do you find out the c case? Here, because once you have the x of t, you know the period, Tp you know, so that means you also know the f. So you can find out the first harmonic, that is e raised to j 2 pi 1, where k is 1, 1 f naught t. So now that you take its multiples by varying the k and you add all of them. But now you don't know what are the ck's. What are these constants which you add to each harmonic. So this ck can be obtained by using this, which is x of t. You multiply x of t with e raised to minus 2 pi L f naught t dt. And you have this normalizing factor 1 by Tp. And this formulation is done over one period from any t naught to any t naught plus Tp. So you can either start from 0 to Tp or you can start from somewhere else. And as long as you are able to cover one period in this formulation, then you, for each value of L, you compute this for each value of L and you get the corresponding CL. Okay, so remember here that this is the summation. Your K is discrete. The summation here is discrete. The K goes from 0, plus or minus 1, plus or minus 2, and so on. It takes integer values. Then one question which we had seen was, does x of t and the periodic signal represented by its Fourier series equate to the same value of at all t? So what we just summarized is that if you have a periodic continuous time periodic signal, it will have a Fourier series. The Fourier series can be represented in terms of complex exponentials, harmonically related complex exponentials, whose period is basically same as the period of x of t. Fine. So you can write your x of t in terms of this series. This series is the Fourier series. So now the question is, how accurate is this Fourier series to represent x of t? Okay. So there are some conditions on which There are some conditions which have to be satisfied for your Fourier series to faithfully represent your x of t. Those are the Dirichlet conditions. This again we have seen. Okay. So you'll see that most practical signals satisfy the Dirichlet conditions. So if you want to see what are the conditions, please look at the textbook. It is there in the textbook. It is also there in the notes. Okay, but there is a problem. The Dirichlet condition will guarantee that x of t, here x of t and its Fourier series will match every value of t except when x of t is discontinuous. If x of t has a discontinuity, then your Fourier series cannot exactly represent x of t at those values where it is not continuous. Okay, so you might remember this Gibbs phenomenon which we had seen. If you truncate the Fourier series, rather than having k going from minus infinity to plus infinity, but suppose you have it from some minus m to plus m, that means you're not taking the whole range, minus infinity to plus infinity, you're taking only a subset of that range. You will see that the x of t and what is represented by the RHS will not exactly match. There will be a small difference. Okay, so that is the result of that is termed as the Gibbs phenomenon. Whenever the x of t is not continuous. So in general, Fourier series coefficients are complex, and there are various conditions. Like for example, when various properties. When x of t is real, for example, Fourier series coefficients will have the coefficients, that is the ck and the cf minus k, are complex conjugates of each other. Okay, so that is when you have ck, this ck and cf minus k, that is -1 and +1, for example. If x of t is real, c1 and c minus 1 will be complex conjugates of each other. So it will be a angle theta and a angle minus theta. Fine. So what did we just see? We just saw that continuous time periodic signals will have a Fourier series. And if you write the Fourier series in terms of frequencies, f, which is, so you know what is already f naught, right? Which is 1 by t, 1 by tp is your f naught. So you can see that they are, because we are looking at harmonically related complex exponentials, the harmonic values are, the k's are going to be values which they are not continuous values, they are discrete values. Okay, so k goes from 0 plus or minus 1 plus or minus 2. So hence the spectrum is going to be a line spectrum. It is going to be line. Line means it is going to be discrete. It's like your probability mass function. It is discrete. So Fourier series. So when you represent a signal by its Fourier series, the spectrum will look like this. The spectra are going to be discrete in nature. Now you can see. Now, okay. So now we said. So if you see this plot here, it's plotting you the Fourier series. And any doubts at this point? Any query? Any questions at this point? Or should I continue? Just want to check if you guys are there, that's all. Okay. Fine. Okay. Yeah, so we said, no, this, so the Fourier series are going to be discrete series. And the spacing between the different frequencies is basically f naught, which is basically 1 by tp, which is based on your period. This is your f naught is the inverse of the period. Now, what will happen if the signal is not periodic? So if something is not periodic, it basically means that the period is infinite. So as the period becomes larger and larger, your f naught, which is basically 1 by period, is going to be smaller and smaller. So when you're looking at signals which are aperiodic, which are not periodic, essentially your line spectra will become closer and closer and closer, and it will become a continuous spectrum. Okay, so essentially it now becomes a your probability mass function is going to become a probability density function. It's going to be a continuous spectrum. That is what is happening in Fourier transform for continuous time aperiodic signals. Right. So as Tp goes to infinity, the space between the lines in the frequency goes to 0. That it becomes continuous. So these are the two formulas for the synthesis and the analysis. So essentially, you'll see that the basic properties and the basic formulation is exactly the same for all the various Fourier transforms and Fourier series. Okay, the fundamental, the only difference is going to be what type of signal you are looking at, whether it is a discrete time signal or whether it is a periodic signal. Okay, so the synthesis formulation, this is like your again representing your x of t using a continuous time Fourier series, which is there here. But right now our discrete sum, which we saw earlier, is now becoming a continuum in omega. Right, x of j omega e raised to j omega t. Your x of j omega are the Fourier transform coefficients, but now omega is a continuous variable. And how to get these x of omegas, x of j omegas, that is done by the analysis formulation x of t e raised to minus j omega t dt. Okay, so remember these formulae. You can remember the essence of these formulae. They look very similar, but you should see that in one case it is e raised to j omega t, in the other case is e raised to minus j omega t. Fine. So this was the Fourier transform. Now we will look at discrete time signals. What was the most important difference which we saw when the signal was discrete time? When the signal was discrete time, we saw that there are specific conditions for it to be periodic. Okay, so every discrete time complex exponential need not be periodic. It has to have a specific condition. The specific condition was that the frequency must be a rational multiple of 2 pi. It has to be like some 2 pi m by n. Okay, so it will be e raised to j 2 pi m by n n, small n. So that has to be, it had to be a rational multiple of 2 pi. That was the first difference. And the second difference between continuous time complex exponentials and discrete time complex exponentials was, for discrete time complex exponentials, only the frequency range minus pi to pi is unique. So the frequencies from minus pi to plus pi are distinct. After that, everything repeats. That is, some frequency omega naught and omega naught plus 2 pi basically are the same frequencies. As a result of this, the spectrum essentially becomes periodic, because with a period of 2 pi, everything is periodic. The spectrum for a discrete time signal is going to be periodic with a period of 2 pi. So omega and omega plus 2 pi are essentially the same. So as a result of this, when you represent a signal in terms of its harmonics for a periodic signal with period n, it will have only n distinct harmonics, because after that it will repeat. The n plus 1 harmonic is essentially same as harmonic number 1. Right? So your Fourier series now becomes, for discrete time case, becomes a finite sum, whereas in the continuous time it was from k going from minus infinity to plus infinity, whereas here it is k going only from 0 to n minus 1, where capital N is the period of your x of n. Fine. So this is how you represent x of n in terms of Fourier series. And to find out the C case, you have essentially the same expression as the continuous time case, x of n e raised to minus j2 pi k n by n. So here also it is a finite sum, 0 to n minus 1. So this is essentially the discrete time Fourier series. Okay, so this is periodic. The spectrum is going to be periodic. And finally, the last thing which we saw was Fourier transform for discrete time aperiodic signals. So we are looking at discrete time signals. We saw the case for periodic signals. Periodic signal will have a Fourier series. So we have discrete time Fourier series when the signal is periodic. And then if it is not periodic, then you have the discrete time Fourier transform. This is essentially the DTFT, which we covered in the class. Okay, essentially the formulation is the same. Only thing is that your x of n, your omega is again now a continuous variable. And but again, like I said, since the signal is discrete, the distinct frequencies are only in the range minus pi to pi or from 0 to 2 pi. So that is why you need to integrate this only between a range of 2 pi. We don't need to do from minus infinity. The omega does not go from minus infinity to plus infinity here. It goes only from 0 to 2 pi or from minus pi to plus pi. So any range of 2 pi is sufficient to get your x of n. And and this is your x of omega. To get these x of omega values, your x of n is now discrete. It's a discrete time Fourier transform. And after that, we will get x of omega. Right? This is your x of omega to get this x of omega here. Okay, I think my computer is going to hang, but let me see. I hope it will work. Okay, so let us just summarize what we just said. Fine. This is a summary. This is important. Pay attention to this. This is crucial. I mean, like the next 4 points, which I'm going to say, is important. Okay. So there are basically two time domain characteristics that determine the spectrum. There are two time domain characteristics. One is whether the time variable is continuous or discrete, whether it is that is x of n or x of t, and the type of signal, whether it is a periodic signal or a aperiodic signal. Okay, so all Fourier analysis is to determine the spectrum. And what determines the spectrum? Two parameters. The time variable of the signal, whether it is x of t or whether it is x of n, and the type of signal, whether it is a periodic signal or a aperiodic signal. So, first point, continuous time signals have aperiodic spectra. Remember that continuous time signals have aperiodic spectra. Okay, this is because continuous time signals have frequencies going from minus infinity to plus infinity, and they are all distinct. Discrete, point number 2, discrete time signals have periodic spectra, because discrete time signals have frequencies which range only from minus pi to plus pi. Everything after a period of 2 pi, after 2 pi will repeat. So omega plus omega and omega plus 2 pi are essentially the same. So discrete time, as a result of this, discrete time signals have periodic spectra. Third point, periodic signals have discrete spectra. If the signal is periodic, then we have a Fourier series. Fourier series means it is harmonically related complex exponentials. Hence, it is going to be discrete. It is not going to be a continuous spectrum. It is going to be like a line spectrum. And finally, aperiodic finite energy signals have continuous spectra. So if the signal is aperiodic and it has finite energies that is a sufficient condition for Fourier transform, then this one has continuous spectra. Okay, so this is summarized in this figure here. Okay, so essentially the take-home message is, if you are periodic in one domain, then you are discrete in the other domain. That is, if you are periodic in time, then you are going to be discrete in frequency. Similarly, if you are discrete in time, then you are going to be periodic in frequency. Okay, so that is captured by this diagram here. This is from the textbook by Proakis. It's a DSP textbook. So this is captured here. Though this top row is for periodic signals, and the bottom row is for aperiodic signals. First column is for continuous time. Second column is for discrete time. Okay, so you look at this one first. So this is the signal is continuous and periodic in time. This is time domain, continuous and periodic, and it will have a Fourier series. And in this case, the Fourier series will not be periodic because it is a continuous time signal. Now you consider periodic signals in discrete time. So this is discrete. So immediately the spectrum is also going to be discrete. the spectrum is also going to be periodic because it is discrete in time. This is periodic, but also we because this is periodic, it will also have a Fourier series, and hence it is going to be discrete. The spectrum is going to be discrete because it is periodic in time domain. So remember this always. Periodic in one domain is discrete in the other domain. So it is periodic in this domain, so it is discrete in this domain. And in this case, it is also discrete in time, so it is also going to be periodic in frequency. So this one is the spectrum here is both discrete and periodic. This is essentially the discrete time Fourier series, DTFS. This is the continuous time Fourier series. Okay. Now you look at aperiodic signals. Aperiodic signal means the signal is not periodic, and hence it will not have a Fourier series, it will have a Fourier transform. And now so this signal is continuous and it is aperiodic. Continuous is continuous in time and it is aperiodic. And essentially, as a result of that, the spectrum is going to be aperiodic. The spectrum is not periodic because it is continuous time and every frequency is distinct. And this is also going to be continuous because we are looking at the Fourier transform. Now the last one is the discrete DTFT, which is the discrete time Fourier transform. The signal is aperiodic and it is discrete time. So that means as long as we know it is discrete in time, it is going to be periodic in frequency. So this is going to be a spectrum which repeats. But now this signal is not a periodic signal, so it does not have a Fourier series. It has a Fourier transform, so it is going to be continuous and periodic. Okay, so this figure captures the essence of all the Fourier analysis tools which we saw. And please go through this and understand it. Fine. So if you have any, so I'll stop this one here, and if you have any queries, you let me know.
Sir, I have one query. So it's not regarding this particular material, but the thing is that, sir, in the timetable it is the slot is 12 to 1, I think, IC 260.
12 to 1.
Yes, sir.
Not 11 to 12.
No, sir.
Nobody has a clash?
I don't have, but yeah.
I don't know. I have to see that. I don't remember the timetable. Yeah, I prepared the timetable, but I forgot. It's D slot, correct. It's 12 to 1.
Yeah. Okay, so I was just going to ask you about why we have preponed or whatever. Okay, so
so you guys don't have any other class at this time?
So I think the civil fourth year civil guys don't have. I'll ask, but I don't know about computer science students from third year.
Okay. Anyway, we stick to the slot. So next time we'll meet from 12 to 1. My mistake.
Yes, sir. Okay, definitely.
Any other queries? Okay, fine. If there are no other queries, we will not have lectures every day. I mean, only when I feel the need for a lecture, I will have a lecture. But otherwise, please do go through the online materials, and I will start uploading some problems. You can go through them and try solving them, particularly the problem sheets. Right. Fine. If there is nothing else, we will stop. Okay. Thank you for attending.